Hello everyone and welcome back to my channel. I am Sahil Sawant and currently I am pursuing my MTech in Computer Engineering at VJTI Mumbai with a background in Electronics and Telecommunication Engineering and research experience in RF systems and radio astronomy. In this series so far, let us recap what we have learned. In episode 1, we saw how signals are variations that carry a certain amount of information. In the second episode, we looked how Fourier reveals the frequency structure. In the third episode, we looked at how sampling must follow the Nyquist. In the fourth episode, we looked at how spectral leakages can affect our frequency interpretation. In the fifth episode, we looked how noise limits our system performance. In the sixth episode, we looked how FIRs and IRs filter involve engineering trade-offs. In the previous, that is the seventh episode, we looked at how convolution explains how systems shape the signals. But now or today, we take a different next step because until now we have assumed something that signal frequency content stays constant over a period of time. But in real systems, it is not possible. Signals evolve. So today's question is, how do we analyze these signals whose frequency changes with time? And for this, the answer is we use spectrograms. Let's think carefully. When we apply Fourier transforms to a signal, you get a particular frequency content. But there is some problem. We lose the time information. We know what frequencies exist, but we don't know when do they exist and how do they exist. For stationary signals, it is fine. But for dynamic signals, it is incomplete information. And incomplete information is more dangerous than what we don't. Now let me explain it to you using a real example. Let us talk about our own speech. When we say a word, the frequency content constantly changes. Vowels have strong low frequency components, whereas consonants introduce high frequency bursts. Vowels are like A, E, I, O, and U, whereas the consonants are B, C, D, F, and so on. If you take a single FFT of entire sentences, you get average frequency content. But we lose our evolution. We need something much more better. And that is the idea behind the spectrogram. Spectrogram solves this by doing something very simple. Instead of applying Fourier to the entire signal, we apply Fourier to small time windows. And we do it by step process. First of all, we take a small segment of the signal. Then we compute its FFT. Then we slide the window forward and we repeat the same thing over and over again. This is called Short-Time Fourier Transform, also known as STFT. Now we have high frequency information at different intervals. A spectrogram is a 2D plot in which x-axis represents the time, y-axis represents the frequency, and the color represents the magnitude or the power of the signal. It tells you at this time these frequencies were very strong. At some other time, different frequencies are getting dominated. It is like watching frequency evolve continuously. Instead of a static picture, you get a moving story. Now let us look at its visual intuition. Imagine a signal that starts at 10 Hz. Now increase it gradually to 100 Hz. In time domain, what we see is that oscillations are getting faster. But in frequency domain or single FFT domain, we see a wide band. In spectrogram, if you see diagonal line that is rising upward, that signal or that diagonal line tells us the whole story. The spectrogram connects the time and frequencies together. Here is something much more important. Window size matters. If window is very short, good time resolution, but poor frequency resolution. If the window is too long, good frequency resolution, but poor time resolution. This is called time and frequency trade-off. You cannot maximize both simultaneously. As I told you earlier, engineering is all about balancing and stuff. Spectrographs are used in audio processing, in which we require it for speech recognition or we require it for music analysis. Now talking about radar systems, we use Doppler shift corrections. In power system, it is also used in transient detection. In biomedical engineering, EEG, electroencephalographs, evolution is determined using this. In radio astronomy, in the projects that I did, solar radio burst and transist events exist. When I worked with radio signals, spectrograms helped identify time localized and frequency activities. Without spectrograms, these patterns remain hidden. Notice how everything is connecting over and over again. Let us talk about sampling. It ensures digital capture. Fourier reveals the frequencies. Windowing reduces the leakage, whereas convolution defines the system's response. Spectrogram combines all this: windowing, Fourier, and sliding analysis. Signal processing concepts are not isolated, they are built on each another. Spectrogram is powerful, but it assumes a fixed window size. If signal has very short spikes or very slow threads, fixed windowing may not capture the efficiency. This leads to next evolution, that is the wavelets, which adapt resolution dynamically. But that's for our next episode. If you remember one thing today, let us remember that Fourier tells us what frequencies exist, and spectrogram is telling us when they are existing. Real signals are very dynamic. Engineers must analyze signals in both the domains, time and frequency domains, simultaneously. In the next episode, we will explore more about what we know as wavelets, because sometimes your spectrogram is not enough to analyze the signal. We need an adaptive resolution. We move from static windows to multi-scale analysis. Welcome back to Signal and Stars.